Welcome again, everyone, to solar-powered IoT, where our goal is pretty straightforward today. We want to help you build more power-efficient IoT products by taking advantage of this magical free energy we get from the sun. We're going to do that through the lens of power-efficient communications and properly sizing your connected solar panels. And I was really thinking about how I wanted to frame this webinar for y'all, and I think it was Jeff who said something like this during one of our calls. When you're building a power efficient product that's supported by solar, at the end of the day, you're doing two things. You're improving your uptime, and when solar is really done right, you are legitimately lowering your BOM costs. And I think you'll see these two concepts kind of play out today. First, if you have any questions during the presentation today, just know you can ask those in the Q&A panel provided in your Zoom UI. We're going to actively answer as many questions as we can throughout the presentation. If we have time at the end, maybe we'll save some of the better questions, but we will do our best when we're not speaking to answer your questions. And just to get ahead of one question that always comes up, is it being recorded? Of course, it's being recorded. We'll put it on the Blues YouTube channel at this URL. You can also choose to subscribe to the channel if you want to, and you'll be the very first to see the video as soon as it's published. Now, some quick speaker introductions in the order in which they will appear today. First is me. I'm the one talking now. My name is Rob Lauer, and I'm Director of Developer Relations here at Blues. With me today is TJ Van Tol, who's our Principal Developer Advocate, as well as the aforementioned Jeff Crystal, who is COO of Voltaic Systems. So thanks in advance to both of you for being part of this presentation. All right, high-level look at our agenda today. So we're going to frame everything around a real-world solar-powered and wirelessly connected IoT project. So that's going to be the thread we follow throughout our journey with Voltaic and Blues. A big part of that is hearing from Jeff on right-sizing your panels based on power profiles, geolocations, other things you may have never considered. We're also going to look at some Notecard power fundamentals and get some tips on lowering your power profile when using the Notecard for wireless connectivity. Now, really quick, what is this Notecard thing even? I do know that a good chunk of you are new to Blues, so give me just 2 minutes, probably less, to give you a quick primer, because Blues is really all about making low power wireless connectivity much easier. And we accomplish this primarily through the Blues Notecard. The Notecard you see here enables wireless connectivity for your IoT product, but it's not just a modem. It does contain a radio, components, circuitry. It really makes it function as a standalone wireless connectivity module. What does that really mean? Well, I always like to frame it as occupying this boring space in the middle here, this part of cloud enablement for your product that you probably don't want to deal with. You're the expert at building your product. You're the expert at your cloud application, whatever it may be. We provide that infrastructure in the middle, that seamless bi-directional data flow that you need. Now, what gets people pretty excited about the Notecard if you're new to it, the cellular Notecard we offer provides global reach, ships prepaid with 500 megs of data, 10 years of service. There's no monthly SIM fees, anything like that. You can get your device's location through the onboard GPS module or through a feature we call Wi-Fi triangulation. Built to be low power, it's obviously pretty important today, consuming anywhere from 8 to 18 microamps when idle. This depends on the Notecard type you are using. We'll come back to this later. That is microamps, right? Or no, yes. See, now I've got myself confused about micro versus milli. This is milliamps. Yes. The smaller one. Ridiculous.
Microamps.
Micro.
Microamps, yeah.
See, we talked before this started. It's like I always conflate the two. Anyway, you may look at that M.2 connector at the bottom as well and be like, how am I going to integrate that into my PCB? Well, you're going to do that through a note carrier, which acts as the interface between a note card and your chosen host, which can be any MCU or single board computer. Plenty of note card options to choose from, depending on the radio you need. They're all swappable in terms of that physical connector, that M.2 connector. And the fact that you use one JSON-based API for the same way across all radios. And if you haven't gone there yet, you can check out our developer guides, docs, all that good stuff at dev.blues.com. Now, with that kind of blitz of information, let's stop sharing and send things over to TJ for the real fun stuff.
Yeah, so what I want to do is introduce a project that I built, and I built this about a year ago, and we're going to use this to sort of talk through some of the tips and different techniques that we have today. Now, this is a CO2 monitor that I built for my house. I wanted to get alerts for when I'm stuck in the office and like my wife is here, the CO2 levels get really high. I wanted to get alerted when basically there was a point at which I should ventilate my house a little bit more and whatnot. So I've got a handful of these devices scattered throughout my house. I've got one in my living room, one in my bedroom. I've got a testing one that I've been using to run experiments that's sitting actually right there on my desk that I can show you later. But what I want to focus on today is that you'll see that I also put one outside. And I did this because I wanted to have a baseline CO2 level. And I also wanted to use this cool little enclosure that Voltaic makes that I've got over here. It's got a little solar panel on the top of it, and it is wired to a lithium ion capacitor here. I can also bring it up on my screen because this picture might be a little bit easier to see. And this works really nice into no card designs because it has these JST connectors. So basically, one end of the JST goes to the solar panel. The other one here, you can just plug into any Blues note carrier. And it's pretty much the easiest way to build anything solar powered with the no card ecosystem. But when I did this, so I've got this outside, and actually, I'll bring up a picture because you'll start to see one of my problems. This is what it looks like outside right now. And one issue I had is that occasionally this thing normally runs fine, it does its thing, but yesterday you'll see that it went offline for a little bit because the power started going a little bit low because it was completely covered with snow. And the problem overall is that I built this very, very naively. When I put this thing out into the field, in fact, when we first started talking about this, Jeff asked me reasonable questions like, how much power does it use? And is that solar panel appropriately sized? And I looked back and went, I don't know. I just kind of put it out there and just hoped for the best. So what I want to do is in the context of this project, I'm going to show you two different versions of the firmware that I've got. And I'm going to start by just briefly showing you the unoptimized version of firmware. So with no card, and don't get caught up too much on the specifics, I don't need you to parse the exact C code. But with no card, you can write firmware in a number of different languages, a number of different ecosystems. This is a very basic Arduino firmware program. And this is almost like what you might build on your first no card project. Really, all this thing is doing, so in Arduino, there's two functions. There's a setup and a loop. The setup is doing some very basic configurations. It's telling no card to send data out every 60 minutes in this case. And then later down in loop, this is where it's actually going to read from the sensor. And then it's going to queue it up on the no card and send it out over here. And then, and this is the key part I want to highlight, it doesn't try to do any magic related to low power, making things sleep or anything. It just delays for an hour. So basically the no card's always on, the host cards, the host MCU is always on. Then every hour it takes a reading, it queues it up on the no card, and it just sort of chills outside. Now, when Jeff asked how much power does this use, I did not know, but I did know that I had the tool to figure that out. Because another tool that we make at Blues that I think is really, really useful for things like this is called the Blues Mojo. I've got a picture of it here. It's quite small. I'll hold it up. I don't know if you'll be able to see it, focus on it. But it's quite straightforward because it's got these two JST connectors and it's got what's called a Coulomb counter in here as well. And the idea being this thing sits in between whatever's powering your product. So either in my case, this was a LiPo battery that I've got sitting over there. It could also be the lithium ion capacitor on the enclosure. But you see the pass through before this gets to my no card and no carrier. And then it's also got this quick cable because this is how the no card's actually going to read from Mojo through the quick cable, and then the power passes through here so that you're measuring the power consumption of your product as it's running. And the cool thing about this is that you can deploy this in actual real world scenarios. So you don't have to take a measurement that is tied on your desk when it's running. Like I could actually take this, put this outdoor in my enclosure and get real world values from this running from my device. And I'm not going to go over every last detail in the firmware to make this happen, but just to briefly touch on it, the way you use Mojo with Notecard. So Notecard has this JSON-based API. There's a very simple request you can use to get the power consumption that has occurred that Mojo has basically detected. This milliamp hour value that starts at 0 and counts up. You can reset this milliamp hours counter by setting this reset true flag. And so essentially, just to put everything together, if you want to just get a sense of the power consumption of your product and you are using Notecard, you could toss a Mojo into your product in between your power source and your device. You can let this milliamp counter roll up and you can just get an idea of the power consumption that you are using. So in the case of my very unoptimized firmware here, that's sort of like our 101 level Notecard project, what I did is I let this thing run for a while. And in fact, if I do my a file here and I do underscore log.qo, this is how Notecard is going to report that data to our secure cloud backend Note Hub. And you'll see I have this running count of milliamp hours coming in. Now, from here, what you can do is you can use this export functionality in NoteHub. So NoteHub has this ability. There's different ways to get this data. NoteHub has an API. You can route this data out. But for this sort of analysis, I like spitting things out into a CSV format that I find makes it a little bit easier to evaluate. And if I bring up my export, the CSV that I brought up earlier, I've got this nice running tally. So I've got the amount of power used, I've got my voltage of my device, in this case, my battery, and then also this timestamp. This is a Unix timestamp that gives the number in seconds. And what I basically did is down here in my write-up, I'm not going to do the math for you. Not going to do the math for you live. I'll just show you here that I figured out that I used this many seconds, which is I've let this first version of the test run for 16 hours. And the milliamp hours, in this case, I used 644, which mathing it out meant I used about 950 milliamp hours in a full day of letting this product run outside, which is not the world's most efficient sort of embedded product. But I thought it was nice to give me a baseline of if you just take a very basic Notecard firmware project, you don't put any effort into optimizing it all, you just kind of throw it out there. This gives you a rough sense of how much power that thing is going to use. Now, what I don't know, and I'm going to use this as a way of transitioning to Jeff, is what that actually means. For this guy, does that mean does this product have any hope on this? Do I have to optimize it? Where do I draw the line? So Jeff, I will pass it to you and let you take it from there.
Can you first, so tell me in this location,
Yep.
um, is it pointing south or is it pointing some other direction? Do you know?
It's mostly south. You'll see that like south is just a little. It's
Oh,
south-ish. You can see that I obviously optimized around this is where my deck is, so I took the direction that's south-ish, but
yeah.
I did not totally measure it out perfectly.
How much of the day do you think will that object be shaded by the building or trees?
It's quite a ways away from the building, if you can see where my garage is here. And these trees do get it some part of the day. So I'd say, a handful of hours for tree cover. I don't think any for the house. I don't think the house reaches out there. But you could probably subtract a few hours for tree cover. Not this time of year though, because leaves are all gone.
And are you worried about anything else, vandalism from neighborhood kids or any other traumatic events around?
No, just the snow, basically, because I don't have a great way of protecting it against that. I thought about, I could put up some sort of cover or try to, but it's kind of hard to completely take away
Yeah.
from that.
So the good thing about that panel is actually it has pretty low surface energy. So the snow will eventually, will fairly quickly slide off.
Yep.
And it's using an EP's chip in there, which does really well in low light performance. So I think overall, I think you have a good start from that side. From the power production side or consumption, you're way off the mark. So the basic sort of formula we're doing, and I don't think it's confused. It should be confusing to anyone. Is that we need to produce more power on average than we consume, and we're actually approaching the winter solstice, which is sort of fitting because when we think about designing for solar, we don't really care about how much solar we produce in the summer months. We care about how much we produce in the worst month of the year. So right now, December, January, and then sort of February, we start to crawl out of the hole. But we're going to have a lot of short days. In places like continental Europe, you're going to have a lot of low hanging clouds. So there's just not that much energy available. And so when we think about designing the system, we need to get through this month. And if we get through this month, then sort of the rest of the year becomes easy. So the way that we think about it is how much energy is hitting this panel. And so a lot of times, we'll get people that will wildly overestimate how much energy is available. They'll say, oh, it's, I'm in Texas or I'm in Florida. It's really sunny here. It gets 8 hours of sun a day. So if I have a 1-watt panel, I'm going to produce 8 watt hours of energy a day. And the reality is, so we have a solar panel, this, sitting there. This is 0.3 watts. Actually, let's get a 1-watt panel. So we have a 1-watt panel sitting there. The sun is moving across the sky. And the fundamental way that we think about how much energy is available is this panel produces 1 watt when at 1 full sun, which means we're at the equator, 25 degrees Celsius, and the panel is perfectly normal to the sun's rays. In that case, it's going to produce 1 watt. Any other angle, any other lighting conditions, it's going to produce less than 1 watt. So what we have a series of tools that'll show us, as well as sort of experimental data, over time, how much energy is this going to produce on average per day. So this panel, if I'm in the continental US, if I'm in Florida, a lot of days it'll see sort of a max of 3 to 3.5 days, average 3 hours of sun a day. So sun moves across the sky. So 3 hours of sun means a 1-watt panel will produce 3 watt hours. So let's look, though, a little more precisely at you. So I'm going to share my screen here. There's a tool that I love to use. It's got a fancy name. It's a PVGIS, Photovoltaic Geographic Information System. And what it allows you to do is select any location in the world, basically, and it'll tell you, and I inputted a 1-watt panel here. So this is a 1-watt panel, and this is, TJ, I'm in Lansing, Michigan here, right? Do you see my little arrow?
Yep. Yeah, looks right.
And so what I can do is say, okay, I have a 1-watt panel and I'm facing it south at 45 degrees. So then in the summer, I'm seeing it'll produce on average 3.8 hours it receives 3.8 hours of full sun. So that 1-watt panel will produce 3.8 watt hours a day. In December, it's less than half. So 1.7 hours of full sun. So a 1-watt panel would produce 3.5 watt hours will produce 1.7 watt hours of energy a day. So not that much. What this tool also allows you to do, so your panel, it's in a fixed location, it's facing south, and it's at a steady angle. So we see applications like this where it's, like, for example, a weather station. A weather station will be in the middle of a field. There'll be no trees. It's going to be, there's an operator there that's going to face it south. What we see often is things are on moving objects. So there's a company called Jang. They're based out of the Netherlands, and they make this IoT tracker. It's for recycling, large recycling bins. And so this goes on the side of the shipping container. And you can imagine over the course of a month or a year, it could be facing any direction. So this could be facing north, it could be facing south. It's going to be anywhere. So we don't actually have this reliability that we're going to always be facing south. It's the same that's true, so like a cattle tracker on an ear. The other thing that we often see is something that's facing flat and straight up. So these are sort of a couple common scenarios, moving through space in a random direction or facing straight up. And so what this tool allows us to do is to say, okay, if instead you were constrained and this needs to be facing straight up, and we put this angle at 0, what's going to happen is this curve of energy is going to become much more like a sine curve. And so instead of 1.75 hours, you're going to get 0.93 hours. So your power production when you go from an angle to flat drops a lot. The other thing that's, and I'm not going to go through all of these, but like if you put it at 90 degrees and you can face it north. So you're going to have a 90 degrees and it's facing north, and it goes down quite a bit again. So these are some of the things that we like to do just at the beginning of a process to sort of ballpark how much energy is available. And so we're going to go back to your number, right? Which was about 950 milliamp hours per day.
Yep.
So that translates to 3.5 watt hours a day. That's 0.95 milliamp hours times the voltage of the battery. In our world, sort of the minimum, we want to be producing on average minimum of 50% more than your power consumption. So if you're consuming 3.5 watt hours a day, we want to be 150% of that. So we want to have the panels be capable of producing at a minimum, again, the bare minimum, over 5 watt hours per day. And so what I'm doing below here, and I'm not going to go through every one of these, but we can pick around different locations around the world. We can say, okay, in San Antonio in December, they're producing, in Texas, the sunny location, Texas, we're producing 3 hours of sun a day. Lansing, Michigan, 1.7. In Amsterdam, 0.9. So you have a third of the amount of energy in Amsterdam right now in the winter day than you do in San Antonio. And then you can also do the same thing where you say, okay, I'm going to place this device horizontally or I'm going to have it rotating. And so if this is rotating or horizontally in Amsterdam, you get less than 0.4 hours of sun a day. If you're in San Antonio, you're getting between 1.3 and 1.9 hours of sun a day. So the amount of sun available and energy available is going to depend a lot on where you are, as well as how it's oriented in time and space. And so then we can go then and we can have a preliminary, and this is preliminary, but sizing of what sort of panel you would need to run this thing. So in your current unoptimized form, if you're in San Antonio, we would suggest a 2 watt panel facing south.
Okay.
If you're in Lansing, it would be a little bit larger, about 3 watts. But if you were in Seattle, you're getting between a 4 to 10 watt panel, right? And so what this means is, our goal, essentially is to have this thing run in perpetuity. And so by having it non-optimized, you can get it to work. You're just going to pay for it.
Yeah, it's cool to see the actual physical size of them too. Just it helps make it a little more real to see. Like there's some bulk to that. The biggest one you brought out there. So
And in some cases, that's what you need, right? I mean, you're running something that
yeah,
consumes that much power. A lot of times it seems like cameras. Then you need that large of a panel. But if you don't, you're wasting money on mounting hardware. You're wasting money on plastic enclosures, size. In general, customers would prefer things that are smaller and less expensive.
yep.
Does that make sense? Everything makes sense there?
It does. How much would people be able? Do you recommend people reach out to you? How much are people able to sort of do that math and figure it out themselves?
Yeah, I would say I think figuring out power consumption is quite challenging. I think there's often a lot of moving parts where people don't necessarily understand, not because they're incompetent, but it's hard to understand how potentially something behaves in the field. Like if something's getting triggered in the real world by some action, you don't know how many times it's going to get triggered. If you have a poor cell signal, you don't know how
Yeah.
in which you don't necessarily know how that's going to impact the power consumption. So I think there's ranges of power consumption that it's hard to get exact. I think getting those numbers, I think sometimes is challenging for people to get a good range. You use your tool. CoreTech makes things, but I think whatever you can do up front to size it properly, I think is valuable. Yeah, I mean, we offer blogs on these things, but normally the introductory conversation, there's just so many weird things that can come up, about a panel design. I think, we have panels that are in the ocean. We have panels that are on cattle. I mean, there's just all sorts of things, things in extreme low light situations where there's variations that it can be useful to talk to people.
Makes sense.
Yeah.
Jeff, do you ever recommend people start with so the case that the enclosure that TJ is using, we at Blues have found it to be, I mean, honestly, incredibly useful, and it's a very pragmatic way to start. Is that a general suggestion for somebody who's getting started with this?
I mean, my general recommendation is to get that number of power um, before you buy any solar. I mean, if you want to buy it, fine. But in general, what I'd rather say is get your number. Get your number of like you're using 10 watt hours a day, using 1 watt hour, using a half. Get that number, and then it sort of frames what size of system we want. Because I think to me, the worst case is you buy this and you need something 5 times the size, and it just doesn't make sense. I mean, I love that system, but for some people, it just may not be appropriate. And so I think getting something that, getting something that is the right size so that it works in the field is important. On the power supply side, the battery we're seeing it right now. There's this again, dark days part of the year. It's really cold. The battery needs, at a minimum for most industrial applications, last 5 days with no sun. But we have customers, especially like in the Nordics, that'll go 60 days. So having a battery storage element that lasts long enough is going to also be less going to have more successful early deployments than if you undersize it.
Makes sense. There are some questions that came in that I could not answer, so I was only half listening to you guys as I was trying to answer all the Q&A. Somebody had a question earlier if anyone has tried the Nordic PPK2 for coulomb counting. Any experience there?
Not here,
all
no.
Right. Sorry. And TJ, I think this question was for you. Interesting logs. The milliamp figure is useful if we know the voltage was at 5 volts. I think you were powered with a LiPo.
Yeah, it's a LiPo on my desk. So,
so more like 4-ish.
Yeah, 3 point.
Yeah.
Somewhere in that range.
And some questions if Voltaic, I mean, we already kind of covered this, but does Voltaic have guides for sizing solar, such as those being shown? There's a couple links that I'm going to be sending out in the follow-up email and that are going to be on my very last slide. But is there anything else specific, Jeff, that you all host on your website that people should know about?
I mean, we have a lot of these things sort of written out in our blog posts, and maybe they're not always as prominent, but I can send those to you.
Okay.
But we've kind of gone through these sizing guides. I think that the other thing that I wanted to share is sort of an interesting tool. And this is going to affect TJ as well. Here is let me just share one more. So the other thing that comes up, and this tends to be more application specific and deployment specific. So we have customers that might have, I don't know, there's some customers that are doing 10,000 systems and they're sitting on, tractor trailers, but then we have customers that are, maybe make 100 and they're deciding where to place these things. And so this is an example. This map is where we work, which is in the Brooklyn Navy Yard. And this app called shademap.app, it allows you to zoom into any location and show how the shade of the building and other structures move throughout the day. And then it'll also allows you to say, okay, I want to know how many hours in the sun is this location. So we had some applications where we're going to place it in Brooklyn Navy Yard, and you could kind of quickly say, okay, this area right behind the building is getting a half an hour of sun a day. And then even in the front part of this building, there's places that get 6.5 versus they get 4.5. So, and then where the roof is getting 9 hours of sun. So when you start to go into specific deployment locations, if you have control over it, looking at something like this in advance can help you sometimes get much better performance. Because we have some customers where they're placing it now, and they place it sort of in bad location, and they have they're getting 50% sun that they expected, which then can lead to downtime. So TJ, if you put your house in there, I don't want to dox you, so we're not going to share your house.
I'm curious though, because I know it's we also because at Blues we also make like an air quality monitor, right? Which I busted out, I had on my desk over here, and it's funny because I've been operating just based off hunches, right? Like I know generally, I know which direction south is, I know where the shade is, but it's still a lot of just guesswork for me. It's like, oh, let's just throw this out here and, really the experiment is just putting it out there and see what happens. And it would be nice to apply a little more science and methodology behind it and less just guesswork.
Right. And often your customers will have a choice. So you might be constrained. It may not all be perfect, but if you can place it in, maybe somebody's moving at 10 feet, 50 feet can have a big difference in terms of performance.
Yep.
Unless you're so oversized that it doesn't matter.
Awesome. Shall we pivot to the note card side of things, or did you have anything else to share?
No, go for it.
Awesome. So let me reorganize my screens here for 1 second. Just because I skipped ahead to show off or to grab some links for people.
How many windows are you rearranging, Rob? Oh, there you go.
So many. It's my problem. I have one monitor and then I'm doing this.
Yeah, it's the downside of your 72-inch monitor you've got down there.
Yeah. Okay, cool. So yeah, I want to pivot to talk a little bit more about how we get the most power of the note card. This is a pretty interesting section, obviously, especially if you're a Blues customer. So when I was thinking through how I wanted to present this, I quickly realized that since we really lead with a low power message here at Blues, these are more core to the note card itself. So it's kind of like taking a step back and understanding what 3 things I think you should know to start. The first thing is we try and preach this, but some people don't listen. The note card was really designed to remain powered on in your product. It barely sips power when idle. You'll actually use more current probably if you power it down and back up repeatedly versus just leaving it powered on. You also need to think of the note card not as a radio only, but as a queue, kind of a storage device that does occasionally sync data with the cloud. All of our note cards have a lot of flash storage for this exact reason, and it's a lot cheaper power-wise to store a lot and then forward all that data once. And lastly, you'll see in my section here that note card already takes care of so many power-related things for you automatically, starting with low power components on the note card itself, but also in the firmware defaults. So let's dig into some specific techniques to make the most, or I guess the least of our power profile on the note card. We're going to start with the biggest, and that is managing your sync cadence, meaning how often are you establishing network connections and syncing accumulated data. Surprise or spoiler here, the less often the better, but there's some nuance there. I also want to talk briefly about picking the right note card. Even amongst our different cellular options, you're going to see some big differences. Then we're also going to talk briefly about how note card can actually manage the state of your host. And then we'll get into the weeds a little bit for a little fun section to see how we can actually disable unused features on the note card itself and then squeeze the last few microamps out of it. So let's talk about sync cadence. So those of you who have used the note card before know that you have different options as to how your note card establishes that network connection, primarily through this mode argument of your hub.set API request. What you see here is me telling the note card to establish and maintain a continuous network connection. Also, every 5 minutes, that's that outbound 5, we're going to sync any accumulated data to the cloud. And every 30 minutes, check to see if there's any data on the cloud that needs to be downloaded to us. Now, remember I said that note card handles some things for you. Even though this config here is far from ideal in terms of low power consumption, at the very least, you should know that note card is smart enough to not even bother making that outbound connection if there is nothing pending to sync, okay? So now I ran some tests on this and found that over 12 hours, our mid-band note card, this is the MB, what is it? MBGLN in this case, that uses LTE Cat 1 Biz, consumed about 157 milliamps syncing data every 5 minutes. Now, it's not terrible, but it's not amazing, right? So a better way forward is to use periodic mode, which tells note card to only periodically establish a connection with the cloud, otherwise disconnect and turn that radio off. Now, in that same 12-hour period, but with 30-minute syncs instead of 5-minute syncs, I was able to get the drawdown to 9 milliamps. Now, I have to do the math, but I think that's comparable to the self-discharge rate of larger LiPo batteries. So that's significant, right? We've already gone from 157 to 9, but we can do better even. And this is definitely a best practice here. We can establish variable sync settings, meaning we're going to sync based on the voltage readings from our power source. So if you look at these V outbound and V inbound arguments, you'll see that when connected over USB, we're going to sync outbound every 30 minutes. But as our voltage decreases, so we take it off a USB, then we're on our power source, whatever it may be, we're going to sync. If the voltage is read at high, we're going to sync every 60 minutes, normal 90, and so on. First question you probably have is how are these high, normal, low, dead voltage thresholds set? You're actually going to tell the note card your type of power source with a card.voltage request. And we have presets for LiPo, alkaline, Tataran, something else as well. But you can actually
Lick.
customize,
Yeah.
like, yeah, you can customize all the voltage thresholds to whatever you want them to be. So this is absolutely how you should be designing no card around your to get that lowest power profile. But if you want the ultimate control over how often no card communicates with the cloud, you can override everything and use minimum mode. This just means that all calls to sync with the cloud come from you in firmware. Now, this doesn't necessarily mean that this is the most power efficient, but it does provide you with the ultimate control. So in summary for this section, I would say use periodic mode, stretch your sync cadence as long as possible. Again, there's about a megabyte of flash storage on every note card, so you can fit a lot of data on there before you need to sync it. All right, so the next is to pick the right card for you and your IoT solution. The image you see here is part of a screenshot from some power profiling I did on our cellular note cards. I realize you probably can't read any of what is on here, but I did find just kind of in summary that our mid-band note cards, again, these are our mid-band, the ones that starts with MB that support LTE Cat 1 Biz, are almost twice as efficient as their Cat 1 and LTE M cousins in certain scenarios. Now, your mileage may definitely vary. Jeff mentioned this earlier, especially based on the strength of your cell connection and other environmental conditions. But you can see all the numbers here on our docs. Just search for low power, and it's at least valuable in terms of looking at the relative differences in different scenarios. Third on our list was to cut power to the host via note card. This is a slightly more complicated topic. I'm just going to kind of go over it quickly here. Long story short is you can make use of the note card's attention pin to manage the power of a connected host by wiring that pin to the host's EN pin. Now, this command uses the card.attn, the card.attention API, to tell the note card to power it on the host. So in this matter, when you're using the seconds argument that you see here, what I'm saying here is I'm telling the note card that seconds is the interval at which it should power the host back on. In this case, every 3,600 seconds or 1 hour. Now, with this in place, we're allowing the note card to idle in a very low power mode with the host also powered off. Then every hour or whatever you set, turn the host back on to take a new reading before returning again back to that low power state. Now, you should know that this API offers different triggers other than seconds to wake up a host. For example, you can wake a host when a note card receives an inbound communication, an inbound note, or when the note card is in motion. There's an onboard accelerometer that can detect motion, or when any environment variables change. A lot you can do here. Again, I'm going to send you to our docs at dev.blues.com to get more detailed information.
I'll
Now,
say too, Rob, before you get into that, that's another reason to keep the note card powered on, because you can essentially in your system start to view the note card as your mission control. So the note card is always running, but it can control the power of everything else, most specifically your host, which is going to be one of the other things that's sipping power. And basically what you're doing with that API is you're configuring what are the triggers for the host to wake up. Either it's seconds, so it wakes up at some interval, or if you're responding to something, you've got a motion detector. I only need to do something if I sense motion. Those sorts of things are things that you can use as triggers through the note
yeah,
card.
great point. So last and definitely least is the ability to disable unneeded or unused features on the note card. Again, since note card is already a power sipper by default, we're really getting into the micro optimizations here, but you should at least know about them. First is that yes, there is that onboard accelerometer on the note card. You can disable it. Just know when you're disabling these things, you're obviously disabling some of the APIs as well. So just a little warning there. You can also disable that attention pin processing that I just covered. On note cards with a GPS module, you can disable that entirely, though you should know that note card is never going to enable that GPS unless you actually configure it to be enabled. You can disable something called aux mode that lets you work with the note card's GPIOs. And lastly, when using the note card Wi-Fi, you can enable the deep sleep mode on the with its onboard ESP32. Now, I actually want to do something that's kind of fun to me, at least, is show this off because it's kind of interesting to me to see what kind of low power state we can get the note card in, but it is definitely overkill for many of our scenarios. So give me one moment here as I switch my video over to my desk, and you're going to
Looks
see
it
my
looks good.
slightly blurry note card here. I'm going to plug this in over USB, and we're going to watch. We're going to watch as it doesn't turn on because I can't get the USB plugged in. There we go. And I'm going to turn on my current ranger here. Handy little tool. And see what kind of draw we're getting. So we're going to see basically, if you can kind of read that, we're getting about 380 milliamps. That's actually, it's high just because USB is plugged in. Because no card is smart enough to know if USB is plugged in, well, we shouldn't worry about maintaining a low power profile. If I then disconnect this, we'll see that number slowly draw down as the capacitance is all drained. And we reach a good idle state of, 12, 13, 14 microamps, which is fantastic, right? Now, let's take this a step further. And I'm going to plug this back in so I can actually switch over to share my browser screen quickly because I've got my note card connected to my in-browser terminal here. And I'm going to run some commands here. The first one is kind of cheating. This is turning hub set mode off, meaning don't make any network connections. It's only to prevent the note card from making a connection while I'm performing a demo. Otherwise, these other ones are what you saw me display on my slides, and I'll go through them again really quickly. So card motion mode stop true means disable the accelerometer. This card at attention off true means disable attention mode. This is going to disable my GPS. This is going to disable the GPIOs on my note card. Okay. Now that those have been sent, let me stop sharing here. And I can unplug my note carrier as well. And as this gets down, we should see that we have saved. So we see now 11, 12. So we've saved 2 whole microamps here by making those changes. So when we're getting like really into the weeds here, you can see that there's a lot that can be done with the note card. But yeah, your mileage.
And Rob, I was paying really close attention because I'll switch over to me because I want to show off what I did next. Basically, is I showed off earlier the sort of unoptimized version of my firmware. What I want to show next is the optimized version. And again, I'm not going to go too much into the weeds here, but essentially this just implements a lot of the things that Rob just showed off. So if I start at the top, you'll see that I'm now using these voltage variable values. So in my case, I'm saying only sync, you'll recall the previous version synced hourly. Now I'm only doing that if there's USB power or if I essentially have high voltage on my battery. And then you'll see that once the battery starts to go down, so if it's at the normal range, I'm syncing every 4 hours. And then further down the line as power starts to go down. The other thing I'm doing, while also turning off some stuff, I'm turning off the accelerometer. I'm not using GPS, which some of these start to become trade-offs because the GPS on note card is actually quite nice, specifically because even though this is a stationary device, what a lot of our customers do if someone walks away with a device, if the device gets stolen, it's kind of nice to have a GPS in there because you can kind of see where it goes. But for power reasons, I'm turning that off. And then probably the single biggest change in here, the one that's going to make the biggest difference, is I'm using this card.attention request to make my host sleep. So specifically, what this is doing is saying when I call this request, essentially I'm pulling the attention pin, which is connected to the enable pin on my host microcontroller. So it's essentially completely cutting power to my host. And I have my sensor connected to my host as well. So it's also going to power down the CO2 sensor that I'm using. You have to be a little bit careful doing this because depending on what sort of sensors you're using, a lot of them require to be, if they have some sort of heating element in them, they have to have power for a certain amount of time to take actually accurate readings. So in the data sheet for the SCD40 that I am using, it recommended waiting 5 seconds. So when my host does get power, I make sure to wait 5 seconds before actually taking a reading. I'm also working on a completely separate air quality monitor, and that thing wanted 30 seconds because apparently to get air quality, you really have to give it time to process. So you have to be a little bit careful doing this. But just the act of shutting this stuff down can make a huge difference. It just makes some logical sense. Instead of powering something constantly, you're only waking it up every hour to do something and then going right back to sleep. And what I did is, so I took all of this advice, I deployed it. I've got it sitting on my desk here, but then I went through the exact same steps. So because I still had Mojo attached, the data was still coming in, and I've got another spreadsheet over here with some smaller numbers. So this one ran for quite a bit longer. I think it's been, I mean, it's actually still running quite right now. And the math on this one was that it used, so I stopped the test for my write up after it was running for 52 hours, so just after 2 days. And at that point, it had used 34 microamps of power, which is, in my math here, a pretty substantial reduction in power. So I wanted to show this. I kind of purposely took like a very unoptimized version and then a very optimized version to show kind of the spectrum of things that you can build and the tools that we sort of give you to both measure that usage and also to configure based off what functionality you need. You can sort of tune that to what you're building.
So TJ, I think sort of in my mind, the point of this is building a solar application is getting
Yeah.
your power consumption low. And then it sort of becomes, I don't want to say easy, but then it becomes sort of a mechanical integration design problem. So you went from 0.95 milliamp hours to 15, it's a
Yep.
huge decrease. That translates to about zero point 0.1 watt hours a day. So you were at 3.5, you went to 0.1.
Yeah.
Before, we're, maybe a 2 watt panel in San Antonio. In Amsterdam, we'd be using this.
Yeah.
Congratulations, this panel will now power it anywhere in the world, even if it's facing this or even if it's rotating through space. So
Okay.
to me, the big cool thing is you drop the power and all of a sudden you've got a panel, a tiny panel. You can use your lithium ion capacitor. This thing's going to work sort of anywhere in the world, even in sort of suboptimal conditions.
And
So
what I like about this too is that what I'm probably going to do, so realistically, because I've got my the crappy version of my firmware out there right now, but I've discovered through doing this that I actually like getting hourly readings, right? So I crank this down to every 4 hours, but knowing that I have some wiggle room here, I know that it'll cost me more power to go back to hourly, but I kind of want hourly readings because that's just more convenient. And I'll probably also turn the GPS back on as well because I feel like I probably have enough space to do that. But again, since I'll measure this with Mojo, measure this with my tools, and just get an idea of what I'm up against.
you can use that functionality that Rob did, which is if the voltage gets low, let's say you have 5 days of really bad weather, your voltage on your LIC gets a little low, you send readings less often. So when you have the energy, you're
Yeah.
sending it all the time. And when it gets a little bit constrained, you crank down the power consumption. And that to me is a very logical, like, so we have, devices like this tracker, and they're sitting on they could be sitting, this one not in particular, but others that are sitting on a shipping container and they're going across the ocean, 10 levels down, they shouldn't be sending any data, or they should be sending data once once every time. So having those conditions to sort of send data when you want and not when you don't allows you to use a much smaller panel.
Yeah, I think especially with my snow situation, because that's, it's not underwater, but it's a similar sort of thing. Like, nothing's going to happen when it's completely buried, but if it can just kind of hang out for a bit, slow down, and then once it gets uncovered, crank back up.
The one thing I want to play, so if anyone's building a solar application, the one other thing that I highly recommend is it's called a solar intensity meter. They're about $150 in the US. If you search solar intensity meter on Amazon, you'll find one. It doesn't have to be the best, but what it does is if you point it at the sun, you take your panel and you point them in the same direction, it'll tell you how much of energy is available from the sun in watts per meter squared. So on a perfectly clear day, you're going to get somewhere around 1,000. On less than a clear day on clouds, it's going to drop down. And so what that allows you to do, so when we talk about our equation of we need to produce more power than we consume, the other sort of critical part of this is how efficiently is the power getting from your panel into your storage element. And so what that allows you to do is say, okay, at 1,000 watts per meter squared, I have a 0.3 watt panel. I'm getting maybe 0.25, 0.27. So I'm getting close to what the panel's rated. If I'm at a cloudy condition, I can say, okay, at 500, it's at 500 watts per meter squared, half sun, I should be getting roughly half of what the panel's rated into my storage device. If I'm not, then I may be throwing power away and my numbers could be off. So sort of all our numbers sort of assume a roughly efficient system. And I think before you start deploying things and sending them out into the wild, our recommendation is that you verify some level of efficiency for the system.
Yeah, and what we see at Blues too is it's all highly dependent on the scale you're working at too, right? If you're just building a pet project for whatever, it's not that big of a deal. But if as you scale, as the number of zeros go up, the amount of planning you can put into things beforehand, before you start producing real hardware, can make an absolutely enormous difference.
Right. That's where the fun comes in.
Yeah, exactly.
I know we're getting to the top of the hour here. A bunch of questions have come in. Somebody had asked about the current Ranger, and I just posted a link into the chat. It takes you to kind of like a website that looks like it was made in the late 90s, but it's legit. We can vouch for them. And related to that Nordic PPK2, somebody did send a message to us saying that they have used it. It's great. They recommend it. So at least one person can vouch for that. Let's see. Oh, I think a question came in earlier about the enclosure that we had talked about earlier. And the question was, does the mini solar panel link directly to the LiPo or to connect to the Blues Notecard, or is there some in-between circuit or PCB? TJ, can you crack that open quick and just show?
Yeah, or I could just sort of bring it up over here. It connects into a what we call a no carrier. So this is boards that we make to house the no card, and it does have a charging circuit in there. So that's what and then that's what ends up powering the no card. I don't know if holding this up is helpful because this probably just looks like a complete mess, but the short answer is it connects to this, what we call a no carrier board.
Were they referring to the one with the white box with the?
Yeah, I think it was the box.
Yeah, so that one has a ease energy harvesting chip inside with all sort of safety protections, and so like overcharge, over discharge, things like that. So it efficiently charges the lithium ion capacitor in all sorts of lighting conditions. And then the cool thing about lithium ion capacitors is that they have really great wide temperature tolerances, and they have really great safety characteristics. So I hope to see more of them deployed in the field. We see, most people are still using lithium iron phosphate, the sort of dominant storage element. I think LICs certainly deserve a look.
Yeah, you can actually ship them, which has been
easy to ship.
Amazing for us. Yeah,
ship anywhere in the world.
Yeah.
I can vouch for the temperature range because we get just about everything here, and it's been totally fine. It's worked great. It's been better than the lipos that have sometimes lose some efficiency in the dead of winter. So
charge lipos below zero. So if you do, you could basically, you can create dendrites in the cell that can then lead to a short circuit. So it's and yeah. So another reason why I think LICs are pretty cool.
Yep.
On another topic, somebody asked about the input voltage range for the note card itself. I had to look that up quickly, but I'm pretty sure it's 3.1 to 5.5. And one last question. Of course, somebody had to ask an AI question. Any experience in using AI to right size your system's power profile? And are panel and battery temperatures concerning? Are those variables you should be concerned with as well?
Um, let's see. So AI to sizing. I mean, you could. I haven't really used it. Probably could be done. It's not. I mean, it's not. It's not really specifically that challenging. I think the details sometimes get weird. Temperature ratings, yeah, absolutely on batteries. Lithium ion, lithium ion phosphate have certain limits where you want to charge and discharge, and so when we build systems, we abide by that. We're building for our we have some larger systems to power things like gateways that we're introducing lithium iron phosphate cells that you can charge down to negative 20C. But yeah, it's always a topic of discussion. On panels, we cycle test negative 40 to 85C. So from a durability standpoint, no concerns. As you get hotter, the efficiency goes down. There's like on every solar cell, there's basically a linear drop as you go above 25C. It's not typically when it's really hot though. There's more sun, so it hasn't really been an issue from a field deployment perspective. It's more just it seems like more of like an interesting fact than a factor in design.
Excellent. That's perfectly timed. We got through all the questions. Just to wrap things up, first, thanks to the speakers. Thanks everyone for attending. I will be sending out again a follow-up email with links to all these resources. You can always ask us questions on the Blues forum at discuss.blues.com with any note card questions. Yeah, with that, have a great rest of your day. Thanks again.
Thanks.
Yeah.
TJ,
Thanks,
nice
everybody.
optimization.
Yeah.